All right, so we were in section 9.3, part 2. All right, so P-series. A P-series has the form nice simple series. Sum n equals 1 to infinity of 1 over n to the p. And if I write out a few terms, this is just 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus dot dot dot. And p is a positive constant. So if p equals 1, what kind of series do we have? What is it?
Special.
It's special, yes. The harmonic. If p equals 1, we have the harmonic series. And we already know the harmonic series. We've proved directly that the harmonic series diverges. We grouped together the terms and showed that certain groups are all greater than 1/2, and we add them all together. So we've shown directly that the harmonic series diverges. We can use the integral test to determine when P series will converge or diverge. We just have 1 over our function would be 1 over x to the p, some exponent. And we'll go through that in just a second. But P series, our rule, we'll state it first, and then we'll come up with it. Just going to write it out again. N equals 1 to infinity, 1 over n to the p converges. If p is greater than 1, diverges if p less than or equal to 1. And we want p positive, so if we were being just a little more strict, 0 less than or equal to p less than or equal to 1. Just to make sure that we're saying p is positive. All right, so let's talk about why. I always like to ask that question in math. Why? So we already said if p equals 1, we have the harmonic series. We know the harmonic series converges. So we're going to use the integral test. And we said yesterday that the integral test, the reason that the integral test works is the integral test makes sure that our sequence of partial sums is bounded. And because the integral test applies to a decreasing function, we're ensuring that our sequence of partial sums is bounded and monotonic. So that's why the integral test allows us to determine convergence. Our sequence of partial sums turns out to be a bounded and monotonic sequence, so it converges. So we're going to say f of x here for our integral test is 1 over x to the p. And we're going to ensure that our integral test applies. 1 over x to the p for x greater than or equal to 1 is positive, right? We're plugging in positive numbers, so we get a positive number. So we're just making sure that our sequence, and I can leave out this equal, greater than 0, that this satisfies the conditions of the integral test. And we're going to argue that this is a decreasing function. So I'm going to take the derivative, f prime of x. What's the derivative of this function. P is our exponent. Negative P x to the P plus 1. There we go. Right, if you think, yeah, so if you think about the other way then. So if our exponent starts out at, if we have P to the negative 1, we would end up with P to the negative 2, right? And is is our function decreasing? Yes, because we said P is a positive constant. So this is less than 0 for x greater than or equal to 1. So our series satisfies the conditions of the integral test. So we're going to apply our integral test. So this is going to look kind of like the homework problem that we just talked about. So we're going to look at the integral from 1 to infinity of 1 over x to the p dx. And I'm going to rewrite this just because it's easier. I'm kind of like Max. It's easier for me to think about it this way. From 1 to infinity of x to the minus p dx. P is positive, so I'm going to write it this way. And this is going to be the limit as b approaches infinity of what's the quantity that we get when we integrate this. I'll start us out, x. What's going to be our new exponent when we integrate this? Go in the opposite direction than we did here. 1 minus p, I'm going to write it as minus p plus 1. And we have to divide by something. When I take the derivative of this, what comes out in front? Minus p plus 1. So I have to put the minus p plus 1 there. So there's my integral. So I'm just going to write it out in steps here. I get 1 over 1 minus p, the limit as of x to the, as x, or as b approaches infinity of x to the 1 minus p evaluated on 1 to b. And this equals 1 over 1 minus p, the limit as b approaches infinity of x to the 1 minus b minus, and I have 1 to an exponent, so minus 1. So when is this going to converge? Yes?
So wouldn't it be x, wouldn't it be b to the minus 3? Isn't x variable?
Yes, you're right. 1 minus p, should be p here. Thank you. So when is this going to converge? When are we going to have a limit as b approaches infinity of b to 1 minus p? When is that going to converge? What do we need for what do we need for this exponent for this limit to converge? For this limit to exist? We need 1 minus p, our exponent. Let's think. I'm thinking about just this. If this exponent is greater than 1, what's going to happen to this limit? It's going to diverge, right? If this exponent is greater than 1, our limit is going to diverge. So what do we need for this? What do we need for this exponent for this limit to exist?
Less than or equal to one.
Anybody have an idea?
P has to be greater than or equal to 1.
P has to be greater than or equal to 1 because what's that going to give me for my exponent?
That's going to, over time, converge to 0.
So if P is greater than 1, 1 minus P is, what does that make 1 minus P? Positive or negative? Negative. 1 minus P is less than 0. So if my exponent is negative, the limit as b approaches infinity, this quantity is going to converge, correct? What's the limit of b raised to a negative exponent as b approaches infinity? 0. So if p is greater than 1, 1 minus p is less than 0, and my integral our limit is 1 over p minus 1. So I get 0 minus 1, so I get a minus 1 times 1 over 1 minus p. So this is going to converge when p is greater than 1. And if 0 is less than p less than or equal to 1, then 1 minus p, and I'm going to say less than 1, I'm going to leave the 1 out. 1 minus p is greater than 0, and this integral diverges. So the series diverges. Yes.
When you have to test p equals 1 separately,
because we would have to test when p equals 1. That's why I took the equal sign off there.
well, I mean, yeah.
Aside from the integral test, you're saying we'd have to use some other test in the integral
Well,
test?
no, we just have to test that way separately, so you get the natural log, because that term doesn't really make sense for p equals 1.
Right. Well, p equals 1, I get a limit of b approaches infinity of 0.
Over 0 because of
Right. Right. So we would so that's why I took the equals off there. We need to test p equals 1 separately, and we've already done in a direct proof that the series diverges when p equals 1. That's the harmonic series. We've done a direct proof. So this shows us that if p is greater than 1, our p series converges, and if p is between 0 and 1, our series diverges. So we use an integral test to show the p series, to prove that when the p series converges or diverges. So the integral test is really the crux of p series. And p series are nice because all you need to do is basically look at your exponent, get your function in the correct form, and look at your exponent. All right, questions? What I want to do next is just look at some series and talk about what test we would use to determine whether or not they converge. So let's look at, we're just saying what test would we use? We're not trying to decide if they converge or diverge. We're just saying what test would we use and why. And we're talking about tests that we're supposed to know now. So what test would we use on this series? That says integral test.
Is that 3 to the n or 3n?
Just 3n. So this one would be a good candidate for the integral test. We have something that we can integrate relatively easily, and I think we did an example like this yesterday. So we could use the integral test. What does your intuition tell you about this series? If we use the integral test, what's it going to tell us? It's going to diverge. So we get the natural log of, essentially we'll get the natural log of 3n minus 2 as b approaches infinity, so this is going to diverge. How about the sum n equals 1 to infinity of 1 over n times the 4th root of n? Diverge, and what test are we using? So we have converge, we said diverge. What test do we want to use? P-series? So we're going to rewrite this. Sum equals n from 1 to infinity. How are we going to rewrite this? 1 over n to the 5/4. So this is a P-series. P equals 5/4. 5/4 greater than 1. So this is going to, we're already done, this is going to converge. So we have a P-series, P is greater than 1. How about the sum, n equals 1 to infinity of 2/3 to the n? Converge, what kind of series is this?
Oh, is that geometric?
Geometric, there we go. R equals 2/3 less than 1, so this is going to converge. And geometric, we know how to find the sum. So we know this converges, we also know what the sum is. How about sum n equals 1 to infinity of n over the square root of n squared plus 1. So someone says it diverges. What test are we going to use? What test so we're putting a kind of a roadblock between the other tests. The ones we've learned so far. Which one could we use of the ones we've learned so far? We're pretending we don't know the other ones yet. Which one that we've learned so far could we use on this? Nth term test, does the nth term approach 0? The limit as n approaches infinity of the nth term? Let me write a hint. U equals n squared plus 1. So what are we going to use here? Integral test. So we can use the integral test on this one. And if we use the integral test, it turns out Max is correct. This does turn out to diverge. How about n equals 1 to infinity, 1 plus 1 over n to the n. What do we want to do with this one? This one's like a gift. Anybody see it? Let me write something out. What's that limit? Careful. We're getting closer to 2. This is an important one. N. They're all n's. All n's. So, by the nth term test, this diverges. This limit is an important one to recognize. This limit is E. We talked about that before, a couple of times before. This limit is E. This came about from calculating compound interest. So this limit is E. So by the nth term test, this series diverges, would diverge. How about, it's important to recognize this limit. This comes up frequently. N equals 1 to infinity, 1 over n times the natural log of n to the third. What test are we going to use here? All right, let me write a hint. So we can use the integral test here. We have 1 over u to the third du. And we could use the integral test to determine if this one converges or diverges. So part of what we're doing is we're kind of collecting a toolbox of ways of determining if series converge or diverge. Part of this is a lot like techniques of integration, where we're learning to recognize patterns, and we see something and it looks familiar, so we recognize the pattern there. So that's part of what we're doing with all of these tests. It's fairly easy if someone says use the integral test, use the such and such test. It's more difficult, and which is how a lot of them will be when we take our test, that you'll be given a series and it'll say determine the convergence or divergence. And you'll have to pick the appropriate test, make sure the conditions apply, and apply your test appropriately. I want to look at these two, and I want to give anyone who is willing to take it a challenge, kind of a challenge problem. Look at these two problems and see if you can generalize the results that we see here and come up with a kind of a generalization of the p-series test, because these two take the same form. we have something in the denominator raised to a power. Here we have n squared plus 1 in the denominator raised to the 1/2 power. Here we have natural log raised to the 3rd power. And we have its derivative there, so we can apply the integral test. There's something that's related, something comes out of this that's related to these exponents. So if you want to, look at these two problems and see if you can come up with a generalization or an extension of the P-series test for problems in this form. Kind of an interesting little exercise. All right, that's all I wanted to talk about today. So our homework.